All right, today we're going to be looking at two vocabulary words specifically that we're going to focus on, circumcenter and incenter. So we're going to look at what those look like on a triangle and what kind of problems we'll see with those. So the first one we're going to look at is circumcenter, and then we'll have incenter right here. So for circumcenter, we're going to define it as the perpendicular bisectors of the sides of a triangle intersect at a point called the circumcenter. So I'm going to write here, perpendicular bisectors. Okay, so let's just refresh what perpendicular bisectors means, because it sounds like a lot, but remember, perpendicular just means that it forms a 90-degree angle, and then a bisector means that it cuts it in half. So what we're specifically referring to here are these segments that are perpendicular to these side lengths and then cut it in half. So if you look, forms a 90-degree angle right there, and then we also cut these sides in half so that they're equal. So these are equal, and these are equal. And then so where all of those lines meet right here, that is the circumcenter. So all of those perpendicular bisectors meet right at that point, and that's the circumcenter. So one fact that we know about the circumcenter is that it's always equidistant from the vertices of the triangle. And equidistant, remember, means equal distance. So meaning that those all have the same length. So basically, all of these lines that we see here from each vertex, so like we have the circumcenter right here, and then this goes out and extends to a vertex here. It extends to this vertex here, and then this vertex here. So those are all the vertices. And that means these are all equidistant. So they're all the same length. So now we're going to list the perpendicular bisectors. So when you're looking for the perpendicular bisectors, you're looking for those line segments that create a 90-degree angle and cut this in half. So it would be each one of these. So I'm going to highlight my perpendicular bisectors just in pink here so you can see them. So I'm talking about this one and this one. And then I'm going to label them. So in any order, really, I have, let's say PF. So that one's PF, PE, and then PD. Okay, and then I'm going to name the circumcenter. So I'm just going to pick the point that it's labeled as. So it's labeled as P, so I'm going to write P. So that's the circumcenter. Now I'm going to list all congruent segments. So all of the segments that are the same. So first of all, you have all of these that were cut in half and they're labeled as the same. So I'm going to label all of those, and then I'm going to label my equidistant lines, all of these other lines that extend to the vertices. So let me start with these guys that were cut in half. So first of all, AD, so this one right here, is congruent to DB. So I'm just saying these are congruent right here. And then I'm going to do the same thing for all the other sides. So right here, BE, we'll say, is congruent to EC. And then the last set right here, AF, is congruent to FC. Okay, so that takes care of all of those outside ones, and then I'm just going to label these inside ones. So I'm going to highlight those as well so we can see the difference. So these pink ones are the perpendicular bisectors. And then these ones are the equidistant lines that extend to the vertices. So you want to notice the difference. These ones are heading out to the vertices, and then these ones are the perpendicular bisectors. So these green ones are all congruent to each other. So I'm going to just label those also. AP is congruent to BP, which is also congruent to CP. So I just labeled all of those sides. So all of those green segments are congruent to each other. So those are basically the facts now that we know about a figure like this. And we're going to solve some of these problems based on what we know. So we're actually not going to be doing every single one on these because our book at this point does not require us to use the Pythagorean theorem just yet. So, and some of these problems do. So we're going to skip a few of these, and we're just going to basically use our knowledge of what a circumcenter is to answer these questions. So let's take a look at number 1. So kind of your job when you see a problem and it says that it's the circumcenter, you have to kind of look back here, look at this information and think, okay, so what does that tell me if something is the circumcenter? The main thing that it tells me is that I cut the side lengths in half. Okay, so that helps me figure out the side lengths if I know that they've been cut in half. And then it also helps me by knowing that all of these line segments that extend to the vertices, that they are equidistant, so they're the same length. So that's how I can figure out some missing measures here. So let's look at number 1. So I'm actually going to go ahead and cross out on this one D and E. So let's just start with those top 3. So it's asking me for TU. Okay, so what I know about a figure that has a circumcenter like this is that this is a perpendicular bisector right here, which means that it cut this whole segment in half. So if this half is 19, that means the other half is 19. So if each half is 19 and you have 2 of them, then we can either think of 19 times 2 or 19 plus 19, which gives me 38. So I used my knowledge of a perpendicular bisector, so cutting that in half. Now let's look at VY. So this little chunk here. So it's telling me that this whole thing, VU, is 34. And then they want to know, well, what's just VY? So if these are congruent to each other, so these would be equal, and they add up to 34, I can figure out what each half is by dividing by 2. And that would give me 17. All right, and then UZ. Let's take a look. So they're asking me now for inside. So they're asking me for this one. And this is a line segment here that is extending from this circumcenter to the vertex. So it goes from the circumcenter to the vertex. So I have to pay careful attention to kind of where it ends. It goes to a vertex. So if I remember from my diagram, all of the green ones, so all of the ones that go to a vertex are congruent. So if they gave me another one, which they did, so they gave me this one right here at 21. So that means that this one is also 21. And so that's 21. And then that's it. So I'm not doing these 2 because that requires the Pythagorean theorem, which we're not going to get to just yet. So we get to just move on from that. And we'll take a look at number 2. So with number 2, there are a couple that I'm going to cross out as well. We're only actually going to do a couple of these. So before I tell you, I want you to just pause, take a moment, and just try to see if you can label those yourselves just by looking at this diagram. You can figure out what those are. All right, so if you gave those a try, then what you should have gotten was 12 and 14. So basically for GD, this whole thing is 24, so we can cut it in half to figure out what half of that is, so 12. And then for BC, kind of the same idea, except opposite. So we know that these two are equal, this one's 7, so that means that the whole entire thing would be 14. So 7 plus 7 is 14. Okay. And I'm actually going to skip 3 altogether. So I'm just going to go right over to Incenter so we can kind of compare those two and see how they are very similar but slightly different. So Incenter. Let's compare, let's write out what that definition is. So for incenter, instead of having perpendicular bisectors, we have angle bisectors. So now we're cutting the angle in half, and you can see that marked there, instead of the side length. So if you kind of just compare real quick side by side, here we had these, here we had these side lengths cut in half. So these are equal, and now we're doing it to the angles. So the angle bisectors of the angles of a triangle intersect at a point called the incenter, and the incenter is always equidistant from the sides. So now instead of the vertices, or like the angles, now we're looking at the sides. So it's always equidistant, meaning that those side lengths are going to be congruent to each other. So let's list the angle bisectors first. So the segments that are cutting each angle in half. So I'm going to label, or I'm going to highlight those two. So angle bisectors, do those in pink. So the ones that are cutting the angles in half are any of these that are extending to the angle. So all of those pink segments. So now I'm going to label those. I've got PV, so there, PC, and PA. So each one of those are the angle bisectors. Now the name, the incenter, same as before. So it's just P, that point there where they're all meeting at, where all the angle bisectors are meeting at. And now I'll list all the congruent segments. So this one's different. Now we are looking at the actual sides of the triangle. So let me kind of show you exactly. So when we cut this in half, okay, we have these two sides right here, and those are the ones that are congruent. Okay, so this looks different than the last figure where we were looking at, you know, the full side length here. Now we're looking and saying these two are congruent because this angle is cut in half. So then these two side lengths are congruent. So what I can write for each one, let me just go through and label the congruent ones like that. And then like that, so you can see which ones are congruent. And then I'm going to label those. So I just did the first one. So AD is congruent to AF. Then I can do BD is congruent to BE. And then EC is congruent to FC. And then, that was one of the things that we said was congruent. And then it said that the incenter is always equidistant from the sides of the triangle. So here's the incenter. Okay, now let's look at it reaching to each side. So it's going to a side, to a side, and to a side. That means that all of those are congruent. So I'm going to highlight those in green. So those green ones are congruent. So we're going to say PD is congruent to PE, which is congruent to PF. All right, and then let's look at some of these practice problems. So again, we're just going to do some of these. We can't do a good chunk of them because of the Pythagorean theorem. So we're just kind of going to look at the simple stuff and then move on. So for this one, we're just going to look at A and B. So P is the incenter, it's telling us. So when it's the incenter, we know that the segments here, the ones that reach out to the sides, are congruent, they're equidistant. And then we also know that the other lines are angle bisectors. So it asks for NP, and we're given PM. So we know that these are all congruent. So if this one right here is 8, that means that NP is also 8. Then it asks for NK right here. So it asks for NK. So remember, like in our image, this angle bisector right here means that this other part over here is also 17. So I just crossed out A and B. We're only going to look at FC and BF since we can get those without the Pythagorean theorem. So with FC, it's asking for this side length right here. So remember, this is an angle bisector, so it cuts this angle in half, which means then that also these side lengths are congruent to each other. So it means that FC would also be 35. And then same thing kind of happens with BF. If we look over here, if we know that EB is 6, then this means that BF is also 6. Okay, and then we're going to stop there with these notes for now.